Welcome to the NPTEL MOOC on Discrete Mathematics. This is the 6th lecture on set theory. Today we shall study partially ordered sets and partial ordering relations. In a previous lecture, we saw equivalence relations. An equivalence relation is one which is reflexive, symmetric, and transitive. Here we consider a relation which is reflexive, which means for every x, if R is a relation that we are considering, we say that R is reflexive if for every x in the domain, it is the case that xRx. And R is transitive if for every x, y, and z, xry and yrz implies xrz. These are definitions that we have seen before. We say that a relation is antisymmetric. We have seen symmetric relations before. We say that relation R is antisymmetric if for every x and y, it is the case that xry and yrx implies x equal to y. That is, if the relation holds both ways between x and y, then x must be equal to y, which means for distinct x and y, the relation can hold only in one direction, either from x to y or from y to x, not both. So here we consider relations that are reflexive, antisymmetric, and transitive. These relations are called partial ordering relations. A generic symbol that we use for denoting partial ordering relations is this. We could write in this fashion and read this as A precedes B. Of course, this symbol is similar to the less than or equal to relation that we use on natural numbers or real numbers or integers, which is not accidental, because the less than or equal to relation on natural numbers, integers, reals, etc. are also partial ordering relations, because we know that for every number a less than or equal to a, if a less than or equal to b and b less than or equal to a, then a is equal to b, which is the antisymmetric relationship, and if a less than or equal to b and b less than or equal to c, then a less than or equal to c. Therefore, all three properties are satisfied by the less than or equal to relationship. Therefore, the less than or equal to relationship is a partial ordering relation. That is why the symbol that we use is similar to the less than or equal to relation. Since this symbol is rather difficult to write, I will interchange it with the less than or equal to. So, depending on the context, you must realize that the less than or equal to relation might refer to another partial ordering relation. So, let us see some examples of partial ordering relations. Let us consider the divisibility relation. On natural numbers. For any natural number a, we know that a divides a. Therefore, the divisibility relation is reflexive. If a divides b and b divides a, then A is equal to B. If A is a multiple of B and B is a multiple of A, then A is equal to B. Therefore, the antisymmetry relation also holds. By the way, the vertical bar translates as divides. So when we write like this, what we mean is that A divides B. And thirdly, if A divides B and B divides C, then A divides C. The transitivity relation also holds. Therefore, the divisibility relation on natural numbers is a partial ordering relation. We say that the set of natural numbers along with the divisibility relation forms a partial order. Why is it called a partial order? That will become clear soon. Our second example is the divisibility relation on the set of integers. Here we find that this is not a partial order. Not a partially ordering relation. Why is this? This is because we know that 7 divides minus 7 and minus 7 divides 7, yet 7 and minus 7 are not the same. Therefore, the antisymmetry relation is violated. The antisymmetry property is violated by this relation. Therefore, when we consider the same divisibility relation for integers instead of natural numbers, we find that we do not get a partially ordered set or a poset. A poset for short stands for a partially ordered set. A poset is an ordered pair SR, where S is a set and R is a partial ordering relation on S. This ordered pair is what is called a poset. Another example, the example of set inclusion. Let us say we have a family F of sets. Then for any A, we know that A is a subset of A. Therefore, the reflexive property holds for the subset relation. If A is a subset of B and B is a subset of A, then A is equal to B. Mind you, we do not use the proper subset relation here. We use the subset or equal relation. And transitivity also holds. If A is a subset of B and B is a subset of C, then A is a subset of C. Therefore, all three properties hold here. Therefore, this is a poset. The family of sets F along with the subset or equal relation forms a poset. Another example is a relation ARB such that B equal to a power n for some positive integer n. Where A and B are natural numbers. So, we are considering a relation on natural numbers. We say that ARB if B equal to a power n. This is also a poset because A is a power 1. If B is a power n and A is B power m, then A is equal to B, where n and m are positive numbers. if b equal to a power n and c equal to b power m, then c can be expressed as an integer power of n for a positive integer. Therefore, this is also a poset. So those are some examples of partial ordering relations and the corresponding posets. So you would observe the duality here. The less than or equal to relation and the greater than or equal to relation are duals of each other, they are inverses of each other. We can consider subsets of posets. Let us say we have a relation R on a set S. Suppose this is a poset, then consider a subset A of S. Then the restriction of R to A as you can verify is a partial ordering relation. So A is an ordered subset of S. So we have so far been talking about the less than or equal to relation or the greater than or equal to relation, which is the dual of it. These we know are partially ordering relations. But what about the less than relation? We say that A less than B or A strictly precedes B if A precedes B and A not equal to B. We find that this is not a partially ordering relation because the antisymmetry property doesn't hold, and moreover the reflexive property also doesn't hold because it's not the case that A less than A. In fact, for every A we can say that A is not less than A. Therefore, this is irreflexive. And for every ABC, we know that A less than B less than C implies that A less than C. So transitivity holds here. So the less than relation has these two properties, reflexivity and transitivity. When these two properties hold, then we have what's called a quasi-order. So there is always a quasi-order which is associated with a partially ordering relation. When the precedes relation is a partially ordering relation, the strictly precedes relation is a quasi-ordering relation. Now let us consider the issue of comparability. It could be that A less than or equal to B for a pair of elements A and B, or it could be that B less than or equal to A for the same pair, or it is possible that neither may hold. If neither this nor this holds, we say that A and B are incomparable. Remember, the less than or equal to symbol here in fact stands for the precedence relation. If neither A precedes B nor B precedes A, then we say that A and B are incomparable. Of course, you will not find such a pair when you consider the less than or equal to relation on natural numbers. But then in some other cases you would be able to find incomparable pairs. For example, consider the divisibility relation on natural numbers. We find that 7 does not divide 11 and 11 does not divide 7, which means 11 and 7 are incomparable. Symbolically we write using 2 bars, 11 is incomparable to 7. So it is possible for incomparable pairs to be there in some partially ordering relations. That is precisely why it is called a partially ordering relation. A partial order, a proper partial order, has incomparable pairs. Therefore, the set of natural numbers with the divisibility relation is a proper poset, as opposed to a proper poset is a total ordering relation. In a total ordering relation, you will not be able to find a pair of elements that are incomparable to each other. For example, if you consider the set of natural numbers along with the less than or equal to relation, you find that for every pair of natural numbers, the less than or equal to relation holds. You take any pair of natural numbers A and B, either A less than or equal to B or B less than or equal to A. It is not possible that these two, neither relation holds between the pair. Therefore, the less than or equal to relation is a total ordering relation. So, let us consider some examples. Consider this set that consists of 3, 5, 30, 90 and 180. We find that 3 divides, let us make this 15. We find that 3 divides 15, which divides 30, which divides 90, which divides 180. Therefore, you take any two members in this, you find that there is a relation, the divisibility relation between them. For example, you take 30 and 180, there is the divisibility relation between them, 30 divides 180. So, the divisibility relation holds one way. Therefore, this is a totally ordering relation. Another example, suppose A is a set. Consider the power set of A if mod A equal to 1, then the power set of A with the subset or equal to relation is a totally ordering relation, because there are only two subsets here. If A happens to be the singleton containing just A1, then there are only two subsets in 2 power A. 2 power A consists of just the empty set and A itself, and the empty set is a subset of A. Therefore, we have a total ordering relation. On the other hand, if the size of A is 2, let us say A is made up of two elements A1 and A2, then we find that the empty set is a subset of the singleton containing A1. It is also a subset of the singleton containing A2, and these two are subsets of A1 and A2. But we find that these two singletons are not comparable to each other. The singleton A1 is not a subset of the singleton A2, and the singleton A2 is not a subset of the singleton A1. So, these two are incomparable. Considering various orderings, let us consider ordered tuples. First, let us consider ordered pairs. Let us say A and B are posets with the less than or equal to relation or any generic precedence relation. So, we have two posets A and B. Let us consider ordered pairs from A cross B. So, we consider any relation between A and B. We say that ordered pair AB is less than or equal to or precedes ordered pair A prime B prime if A is less than or equal to A prime and B is less than or equal to B prime. So this is one possible ordering. So in this case we can say that 2, 3 and 3, 2 are incomparable according to this ordering. Extending this, we can consider ordered N-tuples. We can say that ordered N-tuple A1 through An is less than or equal to or precedes the ordered N-tuple B1 through Bn if Ai is less than or equal to Bi for 1 less than or equal to I less than or equal to N. For every I, it is the case that Ai precedes Bi. That is when we say that the ordered N-tuple A1 through An precedes the ordered N-tuple B1 through Bn. So this is a straightforward generalization of the earlier ordering that we saw for ordered pairs. Now the ordered tuple A1 through An can be thought to be less than or equal to B1 through Bn. Here we are considering another ordering relation. Let me denote it as less than or equal to 2. So according to this ordering relation, we said that A1 through An is less than or equal to B1 through Bn if Ai equal to Bi for 1 less than or equal to I less than or equal to k minus 1 and Ak is less than or equal to Bk. So according to this, if you consider ordered pair 2, 3 and ordered pair 3, 2, since 2 is less than or equal to 3, in the first component we can say that this relation holds between them. 2, 3 comes before 3, 2 in this ordering. So this is lexicographic ordering. For example, if you were to consider all strings of length 3 made up of 3 symbols A, B, C, if A less than or equal to B less than or equal to C, then in dictionary order you would enumerate them like this. This is the first string of length 3, the smallest string of length 3, then this would be the next string of length 3, this would be the next. Now you have a change in the second position, and so on, ending with CCC. So this is a lexicographic ordering of all strings of length 3. So that is precisely what we do here. We say that an ordered N-tuple A1 through An is less than or equal to an ordered N-tuple B1 through Bn according to this ordering if Ai equal to Bi for 1 less than or equal to I less than or equal to k minus 1 for some k, and it is the case that for that particular k, Ak less than or equal to Bk. So we don't look at the positions which are further to the right of k, that is k plus 1 through n could be anything. So these two ordered pairs, ordered tuples match in the first k minus 1 positions, and when you look at the kth position, A1 through An has a smaller value. Therefore, we say that A1 through An precedes B1 through Bn. This is opposed to the previous ordering that we saw. So these two are different orderings of ordered tuples. And then we can consider strings in general. we can consider an alphabet sigma, and we can talk about all strings from alphabet sigma, which is denoted by sigma star. This is the clean closure of sigma. This would of course consider the null string, the string of no length which is made up of no character. Then it will have all strings of length 1, all strings of length 2, and so on. You can form an infinite set of strings from sigma, even if sigma is finite. So this set is sigma star. Sigma star could be lexicographically ordered, which means in dictionary order you would prefer to order them in this way. We will say that the null string epsilon is less than W for any non-empty W. Any non-empty string W from sigma star will have this property. It will come after the null string. Secondly, if U is character symbol A followed by U prime and V is symbol B followed by V prime, where A and B are symbols, U prime and V prime are strings from sigma star, then we would say that U is less than or equal to V, or U precedes V in this ordering if either A less than or equal to B or A equal to B and U prime precedes V prime. Well, these are strict precedences. Of course, often we find a variant of lexicographic ordering, which would be lexicographic ordering within the same length. So this ordering would be like this. If sigma happens to be A and B, just two symbols, then sigma star would be ordered thus. First you enumerate the null string, then we have strings of length 1 A and B, then we have strings of length 2 AA, AB, BA and BB, then we enumerate all strings of length 3 and so on. That is, within the same length we enumerate the strings in lexicographic ordering, but strings will be enumerated in the monotonic order of increasing length. Now we study Hasse diagrams. We say that A immediately precedes B. This notation says A immediately precedes C, or precedes B. What it means is that A precedes B and there is no C such that A precedes C which precedes B. So there is no intermediate element between A and B. So in this case we say that A is an immediate predecessor of B, or conversely B is an immediate successor of A. In a Hasse diagram, we draw the partial order using lines going from below to above. We do not usually place an arrow. When we place A and B in this manner, what we mean is that A is an immediate predecessor of B. So, the less than or equal to relation now flows from below to above. So, let us consider an example. Let us consider the example of set inclusion. We consider set A that consists of two elements A and B, and let us look at the power set of A, which is 2 power A. The members of 2 power A are A itself, singletons A and B, and the empty set, as we saw earlier. So, in the Hasse diagram, we find that the empty set is included in the singleton B, the empty set is included in the singleton A as well. So, we draw lines in this manner to show that phi is less than or equal to B. Here less than or equal to stands for the subset relation, and similarly we have lines of this sort too. So, this is the set inclusion partial order for two member elements. If A had 3 members, we would have elements arranged in this manner. There is only one 3-member subset. There are 3 2-member subset. And we have immediate predecessor relation between AB and ABC. For example, AB is an immediate predecessor of ABC. Similarly, BC is also an immediate predecessor of ABC. Then we have singletons A, B and C. We have edges of this sort. Yes. And then we have the empty set. Let us consider the divisibility relation. On the set 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. The diagram will be drawn like this. 2 and 3 are incomparable, so you cannot have an edge between them, so they are placed at the same level. 2 doesn't divide 3 and 3 doesn't divide 2. Now, when we come to 4, we know that 2 divides 4. So, we have an edge from 2 to 4 in the Hasse diagram. Now, 5 doesn't divide any of the previous numbers, it is a prime, and the previous numbers do not divide 5. Then we have 6. 6 is divided by both 2 and 3. So, we have edges from 2 and 3 to 6. 7 is a prime. 8 is a multiple of 4. 9 is a multiple of 3. 10 is a multiple of 5 and 2. 11 is a prime. 12 is a multiple of 6 as well as 4. There is an immediate predecessor relation between 4 and 12. We do not draw an edge from 2 to 12, even though 2 is a divisor of 12. That is because 2 is not an immediate predecessor of 12. Because 4 is in between, 2 divides 4 and 4 divides 12. So, there is a chain of divisibilities from 2 to 12, a chain of length more than 1. Therefore, there is an edge from 4 to 12, but there is no edge from 2 to 12. So, this would be the Hasse diagram for the divisibility on this set. The resultant partial order will be drawn like this. Then let us consider the less than or equal to relation on the set 3, 4, 5, 6, 7, 8. Here we find that the Hasse diagram has a simple form. That is because this is a total order, which means between any pair of elements the less than or equal to relation holds. But in the Hasse diagram we do not draw every possible line, we show only the immediate predecessor. So, the immediate predecessor of 4 is 3, the immediate predecessor of 5 is 4, the preceding number. In fact, to get the partial order you should take the, you should apply transitivity on this predecessor relation that is shown here. For example, there is a path from 4 to 6 here in this diagram. Therefore, we know that 4 is actually a predecessor of 6. 4 is less than or equal to 6. A maximal element in a poset is an element A such that no element is greater than or equal to it, or no element is larger than it, strictly larger than it. So, if you look at these diagrams, here the set ABC is a maximal element because no member in the diagram is above ABC. Here we find that 8, 12, 9, 10, 7, 11, these are all maximal elements. And here we find that 8 is a maximal element. Analogously, a minimal element is an element such that no element is less than that. So, if you look at these diagrams, you find that 5 is a minimal element, here 2, 3, 5, 7, 11 are all minimal elements. In this diagram 3 is a minimal element, nothing is below 3. So, those are the maximal and minimal elements. We say that an element is the first element A is the first element if for every x it is the case that A is less than x or A is less than or equal to x. We say that A is the last element of the poset if it is the dual of this, which means for every x, x is less than or equal to A, x precedes A. So, if you look at the diagrams here, here we find that 5 is a minimal element and 5 is also the first element. Set ABC is a maximal element, it is also the last element. But when we come to this, we find that it does not have a first element or a last element. 8, 12, 9, 10, 11 are all maximal elements, but they are incomparable to each other. So, there is no element which is a successor of everybody. Similarly, there is no element which is a predecessor of everybody. 2, 3, 5, 7, 11 are all minimal elements, but there is no first element here. Here 8 is a maximal element as well as a last element. 3 is a minimal element as well as the first element. So, from this we know that a first element is always a minimal element, not necessarily vice versa. a last element is always a maximal element and not necessarily vice versa. Let us consider consistent enumerations. Say S is a finite poset a function f from S to the set of natural numbers such that A precedes B implies that f of A is less than f of B is a consistent enumeration of S. So, this is the precedence relation, whereas this is the less than relation over natural numbers. So, for a function to be a consistent enumeration of S, it should be a mapping from S to the set of natural numbers, and it should be so that A precedes B implies f of A is less than f of B. So, we are effectively numbering the members of the poset. So, let us consider the Hasse diagram of a poset. Let us say we have a set of elements like this. So, a numbering so that G gets number 1, ACD gets numbers 2, 3, 4, B gets 6 and 5, and F gets 7 is a consistent enumeration. G is a predecessor of A, G gets 1 and A gets 2, which is consistent, and G gets 1 and C gets 3, and G is a predecessor of C, which is consistent, and G is less than or equal to F, and 1 is less than or equal to 7. So, once again it is consistent. So, you can check that the precedence, every precedence is satisfied for any pair of elements x and y, so that x precedes y, the number given to x is less than or equal to the number given to y. So, here we have a theorem which says that the x is a consistent enumeration for any finite poset A. So, the proof of this theorem is by induction on the size of A when A is a singleton. We will define f thus, f of A equal to 1, and there is only one element here. So, there is no conflict, the enumeration is a consistent one. Now, by induction hypothesis, let us assume that the statement holds for all sets with n minus 1 elements. Now, for the induction step, consider a set A with n elements. Then imagine the Hasse diagram for A. When you look at the Hasse diagram, you will be able to find a maximal element of A. There could be many maximal elements. Let us pick one out. Suppose that is small a. Then if you consider A minus A, which I call set B, we find that the size of B is n minus 1. Therefore, B should have a consistent enumeration. So, let us say G is a consistent enumeration for B. Then a consistent enumeration for A can be constructed very easily. Let us define a function f. F of x will be defined like this. If x equal to A, we will put f of x as n. If x is not A, then x is a member of B as well. Therefore, g is defined for x. So, we will define f of x as g of x. So, we are using the same enumeration as we got before, that is, we got an enumeration for B, we assume B exists inductively, we take that we take that enumeration and then extend that enumeration by setting the function value for A to n. So, A will now be the nth element. So, in the Hasse diagram, we pick out one maximal element. So, in this case, f is the maximal element, and then inductively we number the rest of the diagram. After that, we put f back in place and give f the largest number. So, in this case, that largest number is 7. 7 is the number of elements in the original set. So, the numbering that you obtain in this fashion is going to be a consistent enumeration. Now, let us study chains and anti-chains. So, let us consider a poset. A n less than or equal to a subset of A subset B of A is a chain if every pair of elements from B are related. Which means B along with the less than or equal to relation forms a total order. In a finite chain, there is the first element and the last element. So, a chain is a sequence of elements of the sort. So, you can always find the first element and the last element. If you look at the Hasse diagram of a chain, it would look like this. So, the bottommost element is the first element and the topmost element is the last element. A subset B of A is an anti-chain if no two elements of B are related. So, that is the definition of a chain and an anti-chain. So, let us take an example now. Let us consider the divisibility relation. The set 1, 2, 3, 4, 6, 7, 12, 14, 21, 28, 42 and 84. This is the set of divisors of 84. Then we have, starting from the bottom, we have 2, 3, 7 are all primes, and 1 is a divisor of 2, 3 and 7. So, 1 will be a predecessor of 2, 3 and 7. Now 4 is a successor of 2, 6 is a successor of both 2 and 3, 12 is a successor of 6 and also a successor of 4, 14 is a successor of 7 and also of 2, 21 is a successor of 7 and also of 3. 28 is a successor of 14. 28 is also a successor of 4, because 28 is 4 into 7. So there is no number so that 4 divides that number and that number divides 28. So there is no intermediate element between 4 and 28. So you have to draw a line from 4 to 28. Then 42 is a successor of 21, which is also a successor of 14, and 42 is a successor of 6 as well. And then we have 84, which is a successor of 42, 28 and 12. So this would be the Hasse diagram for this poset. So in this, if you consider 1, 2, 4, 12 and 28, this is a chain. Similarly, 1, 2, 6, 1, 2, 4, 12 and 84, sorry. 1, 2, 6, 42 and 84 is another chain. What would be an anti-chain? 4, 6, 14, 21 will form an anti-chain. That's because no two of these are divisors of each other. Similarly, 2, 3, 7 will also form an anti-chain. 12, 28, 42 also will form an anti-chain. In fact, 1 alone will form an anti-chain. 2, 3, 7 will form an anti-chain. 4, 6, 14, 21 will form an anti-chain. This is also an anti-chain. These are some of the anti-chain. So I will state this theorem without proof. Consider poset P with the less than or equal to relationship. Say the length of the longest chain is n, then the elements of P can be partitioned into n disjoint antichains. That is, the length of the longest chain is n, then the elements of P can be partitioned into n disjoint antichains. As we have done in this case, the longest chain has a length of 5, so we have managed to partition this into 5 disjoint antichains. These are not the only antichains by any means, but this is one set of 5 disjoint antichains. So the proof is easy. I am leaving it as an exercise to you, but to give a hint, you can look at the maximal elements here. In this Hasse diagram, there is only one maximal element, which is 84. So you can take that out, then the rest of the partial order has chains of smaller length, and we can apply the statement to that inductively. So once you partition the rest of the diagram into n minus 1 disjoint partitions, then you can add the maximal elements that you have removed in the first step. And once again, the basis will be found by the singleton set or the partial orders in which there is a chain of length at most 1. As a corollary, we find that for a poset Pn less than or equal to consisting of Nm plus 1 elements, either there is an anti-chain consisting of m plus 1 elements, or there is a chain of length n plus 1. So, let us contradict the assumption that there is a chain of length n plus 1. So, let us say the longest chain has a length of n at the most, then we can partition this into at most n disjoint antichains. So, this is a partition of the given set. We are partitioning it into at most n disjoint antichains. If no antichain has m plus 1 elements, then each antichain has at most m elements. So, the number of elements would be less than or equal to m into n, which is a contradiction because we have assumed that we have m n plus 1 elements. So, as an example, consider 10 women among them there are 3 women who form a grandmother, mother, daughter triplet. So, there is a chain of descendants of length 3. So, among these 3 women, either there are 3 women that form a grandmother, mother, daughter triplet, or there are 3 women, none of whom is a daughter of another. There are 3 women, none of whom is a descendant of another among those 3. That is because 10 equal to 3 into 3 plus 1. So, we take n equal to 1 and n equal to 3 and m equal to 3 here, and from the corollary we find that among 10 women one of these 2 possibilities must hold. So, that is it from this lecture. Hope to see you in the next. Thank you.